Hi everyone. We will discuss today our complex analysis. Why we need the thing that we should ask to ourselves that why we need complex analysis. So let me first clear this. This is very this course or this topic is very interesting because as an EC or triple E student we should learn this topic and I think that maybe CSE student also. Complex analysis is a very good chapter. I think it is very interesting because we will see the range and domain of this complex analysis of the complex valued function that is different from the same real, like when we think about sin x, it's like -1 to 1. But when we think about sin z, the range will be different for the sin z. So we will see in this coming slides. So why we need complex analysis? What we want to see that like the basic complex number like we see is x plus iy form where f z is equal to u x y plus I v x y. So here the complex value function is fz. This is a complex function which have two parts. First is a real part and second is imaginary part. And the both real and imaginary part depends on the x comma y. This data is it depends on two variable x comma y. So these two are a real valued function. So we can say like u and v are sorry real valued function. And why we need a complex analysis, we will we'll mention this also. So we'll first like v is real value function. U is also real valued function. So v and u is a real valued function, and that they combine to give the complex valued function. So this z is complex number that we know, but we want to analyze this. So we want to think about the differentiation, limit, integration of this function fz. So we are saying this is complex analysis. Why we need complex analysis? We know like some integration like minus infinity to infinity x sine x 1 plus x square. This integration will give you pi by e. Okay. But if you will go from the real point of view, like if you integrate like we do in a real analysis, then it will take 2 or 3 pages, or maybe it will be difficult for us to know this value. But if you transform or change the domain from real to complex, so you can easily get this value pi by e. Okay. So if you change the domain from real to complex, you will surely get this value within hardly 1 or 2 minutes, or maybe less than that. So why we are learning this complex analysis? To increase our scope of study of mathematics in some of the fields where this complex function comes, like in electronics, electrical, it comes majorly. But we, as a mathematics student, we should know each and everything of this course or subject. So we will go ahead and see some of the how we will calculate u and v for this function. So let me give you some hint. Like think about uh, fz is equal to z square. So what is z square means? It is nothing but x plus iy square. And from your basic knowledge, this is nothing but 2xiy. So you can see here the u is x square minus y square, and vxy is 2xy. Okay, sir, means we, as I mentioned above, that u and v are real value function. So this whole function is real. But the combining with this I and this real part and imaginary part, we will give this function as z. Okay, sir. So we will move ahead and see how we can analyze this complex valued function from our some basic knowledge of our class 12 and some of the basic knowledge of multivariable calculus. So we will see this uh, in the upcoming lectures. So as we know that we can write z is equal to r e to the power I theta. So function of z means function of r e to the power I theta can be written as u r theta plus I v r theta. Okay. So means here also u and v are real value function of two variable r and theta, and there's two variable x and y. So from our basic knowledge, you can do this. You know, if you want to do, then you can do like take some problem, like take z is equal to r e to the power I theta, and put f z equal to z. It will become r cos theta plus I sin theta. So when you rearrange this term, it will become r cos theta plus I r sin theta. So this is u r comma theta, and this is I v r comma theta. So you can do this for multiple function. I just took this very simple function of complex number f z equal to z, and we get two variable r and theta, and we take the function u and v corresponding to the result that we know. Okay, and we want to do analysis. What we want to do is analysis part. So for that, we'll go ahead and ask ourselves that what about the limit? Okay, so before the limit, let's see what the for limit what you will think. So we will take some z naught. We will take some z naught in the complex plane. Suppose this is complex plane. This is complex plane, and this is a real part, RE, and this is a imaginary part of this axis. So in this complex plane, there are many complex numbers, but if we bound this, if we bound the region, it will come to as a disk, and we can take this circle as z minus z naught, something like r. R is a radius of this given disk. So if you want to calculate the limit of the function of in a very short distance on a point of f z naught, if you want to calculate the differentiation or continuity of the function at z naught, what we have to do is first we go for mapping. First we will do mapping, then we will see how the limit, continuity, and differentiability will comes in our picture. So just for our purpose, we take the disk of R radius having a center at Z naught in the complex plane. So first come to the some mapping like we do in a real analysis. We will take some mapping. Like suppose this is our real part of Z. Maybe you take this is imaginary part of Z, and this is a complex plane, and we know that there is some system that is our function that will convert this fz to this omega, where omega is equal to f of z. This transformation is called mapping. Okay, we mapping this value to this, and this is also a complex plane. The both are the complex plane. So if we will take the say some region in this, we will get some reason around this omega. Okay, so if you take some reason in complex plane, then you will get some reason in our output in different complex plane. Okay, and here omega is what? Here omega is uxy plus ivxy. Okay, so this axis is what? This axis is ux comma y, and this axis is what? Vx comma y. So basically what we are doing, actually we are applying some function, like we can say transformation on z to give some output f of z, which is a two-valued function x comma y, having a real part as a uxy and imaginary part as a vxy. Okay, so what I'm saying to you, if you will took some, if you will take some disk around Z naught, consider this as a closed disk or open disk as your purpose, but we are now taking closed disk. So we of radius r, that is Z minus Z naught is equal to r or less equal to r. We have some domain in the complex plane that this, and this will map to some reason. Maybe it will disk or not, I don't know, but there will be some reason omega naught having radius r. Let's take that the reason we get as an output is a disk, and then this is omega minus omega naught is some r1 radius. This is r1. So what I'm saying, as many as you take a point in the complex plane as an input, as many as you will get in output also. So the main theme is that you take the input around Z naught and you will get some output around omega naught that that you will know. But for a limit point of view, what we will take, we will small the distance between Z and Z naught. We will see further that what we are saying in this, like suppose R is very small, like we can take R is like epsilon, like we know in a real valued function, we know about epsilon delta function. So Z minus Z naught is nothing but this epsilon. So we will surely get some delta. We will surely will get some delta for this fz minus z naught. Okay. So from limit point of view, how we will say this? Like from any path, if you will come from any path, if you will approach this z naught. Okay. If you from any path, if you will approach this z naught, we will get some as a delta as a function. What function? Z minus z naught as a function. Okay. So limit in real value function, we see the limit in from right hand and left hand. In real value function, what we will see, what we are saying is that we saying that limit will exist if LHS of and RHS are equal. Okay, if LHS and RHS are equal, then we say that limit exists. But in this complex analysis, what we have to think that from any path you will come to this point, from any path you approach this point, limit or the value of the function should be same. Okay, if you vary the theta of this complex number, the number you will get as an output should be same. The complex number, that is omega, that should be same. So from a differential point of view, if I will see you that calculate f dash z naught, means there is some reason in this complex plane and there is some function fz. I am saying that calculate where the differentiation of this function at z naught. What we will do, we will take some limit h tends to 0, f z naught plus h minus f z naught by h. This is as simple as we know from the real analysis part. Okay, we will increase z naught plus h, means we are, and you know, this h is also a complex number. This h is also belong to the complex number. Okay, this h also belongs to the complex number. So you don't think like h is a real number. H also have a some expression like h1 plus I h2. Okay, So what we are saying that if you will add some h that is tending to 0, and we will take the limit for the change of the rate of this function z, about the z naught, we will get a differentiation. Okay, so now the things are clear that what we are saying up to this, that we want to calculate the differentiation is whether differentiable or not, whether continuity exists or not, whether limit exists or not. We will see, but there is a simple theorem for this, that is Cauchy-Riemann theorem, and this theorem is very useful. Okay, what the theorem says, we will write this theorem. Right, theorem is, suppose xy and vxy have continuous first partial derivative in a domain D. It is very important. D is a reason that I mentioned the disk, and U and V satisfy Cauchy-Riemann equation, CR equation, in complex plane D. Then Fz is analytic in D. What we are saying that if that real part and imaginary part that we know have a continuous, means it should be continuous. What should be continuous? First partial derivative in a domain D, and U will satisfy CR equation in D, then Fz is analytic. And what is CR equation? CR equation is that del U by del X is equal to del V by del Y. And I'm mentioning you that this U and V are two variable function. So I will write x comma y, x comma y, and function del U by del Y is equal to minus del V of del X in x comma y. So we will do this proof of this Cauchy-Riemann equation, and let's think about this. And the main thing that it will also satisfy harmonic equation. We know that what is harmonic equation. So harmonic equation is del square U by del x square by del square V by del y square equal to 0. The same U and V we are talking about. Okay, and del square V by del x square and del square V by del y square. Sorry, this is also V. This is also U. This is U. Okay, this is capital U. This is capital U. This is V. This is V. Okay. On what is harmonic equation, you will see. You will see. Just I'm writing the equation that if you will prove, you can prove this. It's very simple. If any equation satisfy harmonic equation, it will surely satisfy, sorry, CR equation also, vice and versa. You can think about this. Okay. Uh, Same. I will say that we will do plenty of example in this course, but later do for this function r e to the power I theta. We know that this is u r comma theta into I v r comma theta. So applying CR equation, what's your equation say that del u by del r is equal to del v by del theta 1 by r. Okay, and del v by del r is equal to minus 1 by r del u by del theta. We will do all this expression, we will do all this expression. We will prove all this expression. Just I am giving you, this is r, okay? This is r, this is r, this is u, this is v, this is r, this is minus 1 by r, this is del theta. We are taking partial derivative, okay? We are taking partial derivative of this CR equation. So if you want to apply CR equation in a Euler form, in polar form, then you can do this like, we will prove this also, but we will prove this CR equation and all the harmonic equation in our next lecture. But for today, we can do some problem based on harmonic and CR equation, okay? Uh, then what we can do, okay? So question is, so that e to the power z is continuous function in entire, you will get amazed to know, in entire complex plane, okay? In an entire complex plane, this entire complex plane means you can take any value of z, it will and you plot the graph, you will surely get the function that is a continuous. How we will do this question, okay? So let us think about the solution. So how we can write this e to the power z is nothing but e to the power x into e to the power iy. This is nothing but cos y plus I sin y. If I will ask you ux comma y, this ex cos y, dx is equal to ex sin y, okay? So if any function is continuous, it should satisfy Cauchy-Riemann equation. Okay, so how you can say the Cauchy-Riemann equation? So you can find del u by del x, no problem, sir. Minus ex sin y and del u by del y, ex sin y. Wait. This is del u by del y. Okay, this is del u by del y, and this is del u by del x. Sorry for that. Similarly, you can find for del v by del x, this is ex sin y, del v by del y, ex cos y. Okay, cos. Okay, so and here maybe I have some wrong. This will be cos y. Okay. So you can see for Cauchy-Riemann equation to satisfy del u del x equal to del v del y, it is, and del u del y is equal to minus of del v by del x. So it is okay. So as you know, this CR equation is satisfied, and what the statement says, it should be continuous. The first partial derivative of del u and del x, should, del v and del u should be continuous. So it is continuous also. Okay. So it is continuous and CR equation satisfying. So Fz is analytic in whole domain D. You choose any xy. So we can say that Fz satisfies CR equation, and its first order partial derivative exists and continuous in a whole complex plane. So this fz function is differentiable fz equal to the power z is function is differentiable and analytical in all point. We can find limit in all the points. We can find the differentiability, continuity in all the fz equal to e to the power z. Okay, so I will give you some something like, okay, uh, surprisingly, if you, I will tell you that what is graph of y equal to function of x equal to log x, you will say this, sir, this is a graph. This will cut at 1 comma 0. If I will say you that find domain of log z, okay. So here, the interesting thing is that x belongs to 0 to infinity. Okay, what will be the domain for this? Okay, find domain of z. Okay, maybe you can think like it will be same, but I want some proof. है ना? We want some proof. We can write this log z is equal to log r plus I into theta, where theta is a argument. It can take any value. Okay, theta, this is a principal, theta principal plus 2 n pi. This theta can take any value. Okay, so you think about this. What will be the domain of a log z? Okay, so for today, what we learn the introduction to the complex number, how we can think about the limit, how we can what the theorem for analytic function in fz. Analytic means what the means of analytic. Analytic means we can find limit, continuity, differentiability each and at each and every point. Okay, what is the harmonic equation? What is CR equation? And find the domain. We will discuss in our next class. Thank you so much. If any query in this topic, you can comment me. Okay, thank you very much.